Alright guys, today we're going to be looking at the third problem under the binary search pattern, and we are on our road to master algorithmic questions by identifying the patterns and trying to solve the most important questions under those patterns in JavaScript. And we won't be running our code. For anyone who's new to the videos, we won't be running our code. We usually just walk through our code using example test cases and see how we would do it in a real interview setting. Now for today's problem, it's very straightforward. Let me read it for you. Given an array of integers sorted in increasing order and a target, find the index of the first element in the array that is larger than or equal to the target. Assume that it is guaranteed to find a satisfying number. Now that the interviewer has given us an assumption that every time you're going to find a solution, we would still have to factor in the fact that we need to return a -1 or a 0 when we don't find a solution. Alright, so going by an example, when an interviewer gives you a question like this, it's always very important to first understand it. And so either you could present the interviewer with a example test case, or the interviewer may present you with an example test case. In this case, let's assume we are presenting an example test case to the interviewer. And so let's say we have this array given to us, and the target that's given to us here is 2. Now what should the result be based on the question that was asked? The result here should be 1. Now how is it 1, right? 1 is the index of the first element from the left of the array, which is greater than or equal to 2, right? So 0th element here is not greater than or equal to 2, but the first element here is greater than or equal to 2, so we just return index 1. Now when you look at a sorted array, and when you look at finding a target in an array, or trying to traverse the array to achieve your goals, we always have to consider binary search as a potential solution. Now in our previous problems, such as find occurrences, find boundary, we have always tried to use binary search template and tried to tweak the conditions within binary search to obtain a goal. So let's see how we can do that in this question. Now this question is very similar to the find boundaries question. However, there's only one small change in the condition that we would have to make. Now let me show you what the condition is. Now let's get started with the very basic function in JavaScript, which say first greater element, greater or equal element. Right? And now that we have created a function, let's go ahead and start filling in. Now I would start by writing down vanilla binary search in JavaScript. So again, I would initialize left pointer to 0. I would have my right pointer start at array length -1, and then I would also this time have a result index, which should be set to -1 if we end up not finding a result. And then as we do it, always left is less than equals right, and every time our goal is to find the mid element in every iteration, so we say left plus, it should be burned into your memory by now that we always try to do the method of finding the middle element, middle index basically, by trying to avoid any integer overflows. Now that we have our mid index, let's see what the element in the mid index gives us. We say if array of mid is less than or equal to, or let's assume we do the greater than or equal to target first, right? Now in a vanilla binary search example, we just usually do if it's equal to target, we just return mid. Right? Now we'll see how this is not going to work for our problem, but for now let's assume we do this, and we say and if it's not, then we have two different conditions. Say if array mid is less than target, right? Then we know that our target lies to the right of it. So we do left equals mid plus 1. And in other case, where we know our target is less than array mid, then we know the target falls to the left of the array mid. So we shrink our right boundary and say mid minus 1, right? And now there's a very simple binary search thing that we implemented here. Return result index. This is what we want to return at the very end. However, as you noticed, we never tried to assign a value to the result index variable. And the reason is we are going with a vanilla binary search. Now there's one small observation that we can make in this problem, and that is that even if we find an element that satisfies our greater than equal to condition, so let's go ahead and type out the condition that the question is asking for. The question is saying if any element in the array is greater than or equal to target, it qualifies for a correct solution. So this is what the question is asking us for, right? So every time we try to find the mid element and then we try to find the element that that index holds, mid index holds, we say that it's greater than or equal to target, then we have our solution, right? So logically we should be updating our result index here, and then instead of returning it, just like we do in find boundaries, we want to continue our iteration by moving towards the left, right? And because the array mid could be greater than or equal to target, we know for sure that our target could lie to the left of mid going forward. So we're going to keep moving towards the left, towards the 0th index, and continue our iteration. And so to do that, we would just do right equals mid minus 1, right? We're just saying forget about all the elements to the right of this mid index, and let's only consider all the elements to the left of this mid index. And the reason is we may find a mid element which satisfy the condition, but there could be other elements to the left of this mid element that could satisfy the condition too. And we want the element that has the smallest index, which means the element which is closest to the 0th index. And now that we have accomplished our main condition here, we would still want to modify the existing conditions, right? Now we don't need both of these. We are already shrinking our search space from the right. So let's also cover the condition where we would shrink our search space from the left. Say left equals mid plus 1, right? So if this condition is not satisfied, then we know that the target lies towards the right of the mid index. And so we want to move towards the right. Move towards right. And then here we are trying to towards left. And then we're just gonna get rid of these additional conditions, and finally return the result index. Now let's see how we would walk through an example, right? I would recommend multi-line comments. I would recommend labeling it as walkthrough so the interviewer knows what you're doing, and then get the example here. The target that we are looking for is 2, so let's get that 2 here, right? And so this is what our algorithm does. Now we are trying to explain how our algorithm works, right? Let's make sure the algorithm is in the frame, and initially we set our left pointer to the 0. Let's also index label it 0, 1, 2, 3, 4, 5, 6. Amazing. And now we have a left pointer at 0 and then a right pointer at the very end, which is array length minus 1. And then to find the middle element here, it's pretty obvious that our middle element is 5. the middle index is 3 right here. And now our first condition in our algorithm says if array mid is greater than or equal to target, and our target is 2. Now 5 is greater than or equal to target, so it's going to satisfy the condition. And so in our first iteration, we're going to set result index to 3, and then we're going to say let's move our right to mid -1, which is take right from here, move it all the way to mid -1 right there, and then we get rid of the middle element. Now this is our new search space. Now in the second iteration, we again try to find the middle element, and it's pretty obvious that this is the middle element here, which is index 1. And then we check if array of mid is greater than or equal to target. Well, 3 is again greater than or equal to target. So we update our result index to index 1 from here. And based on our algorithm, we shrink our search space from the right, and we bring our right pointer all the way to mid -1, which is where the left pointer is at. And now our iteration is going to terminate because left and right both pointers have converged to the same index, and we're going to end up returning index 1. Now you saw that how our algorithm handled the case where we found our target in the very first iteration. However, we still continued to move towards the left until we either hit the exit condition here, or, well, there's no or here, right? We have to go through all the iterations, and the maximum number of iterations that we could have, given we always try shrink our search space by half, is log O of log n, right? So number of iterations that we are making is equal to log n, where n is the length of the array, right? And so this was a very simple walkthrough of the algorithm with an example. You could try different examples in the interview, but at the very end, always remember to state clearly what the space and time complexities are. So we should always usually try to label it. We say time complexity here, since the number of iterations is log of n, at max, our time complexity is going to be log of n. Now space complexity is going to be O of 1, which is constant space, right? Because we're not using any additional data structures to store the values. And so this was pretty much it. We saw how we can use binary search in a setting where we need to find the first element greater than or equal to the target. And this is one more simple use case where you saw how we can modify binary search template and achieve our goals in the interview. Thank you so much, guys. See you in the next one. Bye-bye.